each tree or whatever they see, each building, it's described really in great detail in this. Everything is described really in great detail in this database. So this is a database that is constantly being updated. And since it reflects our environment, so this is the world about around us, if we think about the world around us, it's of course our network, because if we are going through streets, to pavements, through roads, this is a network, and maybe it's a good idea to analyze this network and try to understand its properties. And there's a second thing. If we talk about the urban space, we can think about attractiveness of the urban space. So there are things like schools, businesses, universities, restaurants, places where you can buy food, go to the doctor, visit pharmacy, and so on. All of this information is available freely in OpenStreetMap, and this is a kind of data that is sprawling around this graph. So on the one hand, we have a graph representing the environment, but then we have lots of data about edges, about nodes in this graph. And our goal is twofold: is to build a database, probably to make available for download like the entire United States or the entire Earth. So all the places of interest, and also try to analyze this graph. So there will be few Julia tools that I am or we are developing. They are at different stages of development. But first thing, so this is how OpenStreetMap looks like. Basically, the idea is the following: that you can go to the website. So this is the area around. This is the area here around the Fields Institute, and you can select some piece of area, and then you export data. Of course, if I need to have entire Ontario, then I wouldn't click. I would just, there are ready databases because it's many gigabytes in size. And then when I export such data, I'm seeing something like this. So the first basic element are nodes, and these are vertices of my graph. So each place is on Earth is a node in OpenStreetMap data. So I have this latitude, I have this attitude, longitude, and an identifier of the node. So this is actually the area around. This is actually an area around Fields Institute. So this is the first piece of information. So these are points, and the second piece of yes, it's 1 point. And some of those nodes, exactly to be more exact, some of those nodes can be interpreted as edges of graph. Others perhaps not, because a node might be a tree. So maybe I do not want to include a tree in my graph, but I would like to know that this is a place that it has, some trees, it's green, so maybe it's more attractive for me to walk. So if I'm going to interpret an edge on the graph, I can use that piece of information. Each building responds to several nodes. Yes, it will be on the next slide. Okay. Okay, so the nodes are then connected by edges, of course, and those edges are called ways in this those edges connecting nodes are called ways in OpenStreetMap. And basically you have a set of edges, and here you have the building of Fields Institute. So actually this is the building you are sitting on, and each corner of the building, somebody took a GPS and exactly measured where is exactly located each single corner of this building. They all have their corresponding data points, and there we are then all of these data points are collected into the buildings. Okay, so this is our actual building of the Fields Institute. And the great thing is that all developed countries have been mapped in this way to very, very great detail, because in the previous slide you could find the coordinates of this point with exact latitude and longitude, and here are all the corners of the buildings of the Fields Institute. Okay, so each piece of information is here. Now, this is Fields Institute, so if I'm talking about road network, it won't be part of the road network. I would rather consider as a point or a place when I can go to lecture, so it's an educational institution. But of course, similarly, if I have road, the road will be described in a similar fashion. So I'm going to have points, ways, and then they're connected by road. There is also third layer of aggregation, which is called relations, which is kind of similar to ways. When you have something of more complex, I would say the area of Toronto or a district. So something that combines, or a university campus. So university campus might combine several buildings. So a single building was away, like here the building of Fields Institute, but the entire campus of University of Toronto would be a relation in this database. Okay, so we have this kind of database, and we have tags. Okay, so tags, as you can see, they provide very detailed information about each building. So if you have a Starbucks, you have very often opening hours. You have name, address, and so on, that it's a cafe, whether it's accessible for disabled people, and so on. So there is really a huge amount of, there's a very often huge amount of information about each place. Okay, so this is a graph. So the word around is a graph, and there is plenty of metadata that we can use, to start describing the graph. And I've noted that it seems like there is no useful database of big areas. There are some small databases, or there are some commercial projects trying, to offer one city and so on. But it seems that there is no database like of entire Canada, of entire United States, or entire planet that is in nice and processable way, okay? Because those XML files are very big. So the idea is to build such a graph and to analyze this kind of the graph. So there are a few related libraries. One library is a Julia library that I'm maintaining, which is OpenStreetMap X. What it does, it takes a portion of a map and generates graph representing road network. Okay, and it's kind of stupid library. All it does, it takes a map and makes a graph. So this is a graph, it's a Julia graphs.gl graph that can be analyzed for its graph structure. I will be mostly, on the next slides, I will be mostly showing vertices rather than edges, because edges are the roads. So sometimes I'll be also using a map as an overlay, then you have the edges. But I will be mostly focusing on visualization of vertices, because there will be too many of them. But anyway, this library can take any piece of map in this format. So just to recall, you select some area, you click here, you have the export button, so you export this area, you get some huge XML files, and then you can transform it to graph using this library. Now, I've been using it for some other project, like this is a project, for example, simulating some part of transit in Toronto and movement of people around the city. So you can build this kind of models, but this is not the goal, but just the capability to show you it's a graph. Okay. So the second library, it's a graph of graphs.gl. So this is a Julia library for manipulation graphs. So this is the next thing I'm using. And there is another library that we have we are now developing with Julian, and actually we have also developed some small part during this workshop. That this is a library specially designed for extraction information of points. And so this is the area, so this is kind of input data. So this is the area around, the area around Fields Institute. Now I have classified those points, I can show this more interactive. Okay, so this is the area, this is the area around Fields Institute, okay? And these are all points of interest. I could, from some classes that interest me, so I'm looking for a few classes like transportation, healthcare, a grocery store, and so on, entertainment, shopping, and so on. So these are all the points of interest, so these are all interesting things that are around Fields Institute from those classes. And then we have developed an attractiveness database, which basically can be generated from any graph, from any maps, from any area. This is, for example, attractiveness for Fields Institute. So these are the coordinates for the Fields Institute, and there are some measures. I will tell in next slide that it's now being aggregated in some quite primitive way, but this is a set of measures. So we are measuring attractiveness of education, availability of education, which is very high in this area, of course, availability of parking, which is not as high, shopping, there are lots of transportation, healthcare, there are several hospitals in the nearby, so it has created lots of points. Yep. Okay, so the edges is the road network. So I'm not plotting the graph actually. Like I said, I'm not plotting the edges is the road network. And this is a piece of data I'm going to inject into the graph. So this graph, so if you think about road network, is immersed in a city. So I want to use this attractiveness information and apply it, inject it to as actually I plan to, so now I'm injecting is as weights of edges, but because I have modularity function that works on weights of edges, but then I also want to inject this on vertices. So basically, this is a vector of weight. So if I think about this location of fields instituted as a node in this graph, in the system, then I have several parameters, several weights. Okay, so I have a kind of weighted graphs, and these are all the weights that are representing the fields institute. Okay, so and when I zoom them, so this one is education, so this is a university building, so there's a hospital here. There's some restaurants. Now, depending on the importance, which I have selected somehow arbitrary, but it's parameterizable. Depending on the importance, I have smaller and larger circles, and I have ranges of importance of those objects. And the goal is, so I have the network representing the road network, and the goal is to inject this attractiveness information into the road network. Okay. So yeah, this plotting is done by the program. So the underlying plotting is here. So the map itself is, the map tiles have been generated. There are open source map tiles that you can use as a background for your plot. So this is essentially a scatter plot using geographic coordinates, but as the background I'm putting the map. But also I have a graph that is exactly corresponding to the entire road network. But I'm not showing this graph because I would not be able to see anything. So the only slide I have this graph corresponding to the road network is here. So I have this graph, it's there, but I'm not showing it on the other slides because of the readability. The colors, let's see what's what. So this is, it's bank. Which dot? Oh yeah, it was from the different project. Yeah, it was a public transport, and here I have also public transport. Here it's the stop position. So this is the tram. It's street card on College Street, and here is the tram stop at College Street. So it has different color and different shape, but here it is. Okay, so here is the tram stop, and here is another tram stop. And basically the idea about attractiveness is if I am close to a tram stop, it's more attractive because I can use public transportation. At least it's more attractive in the dimension of transportation. Okay, so I have dimension transport, and then this area is more attractive. If there is a parking spot nearby, then area is more attractive in the terms of parking. And then I apply this attractiveness to each small node in the graph that is underneath. Okay, so I have too much data, so I didn't know what is the best way, the best way to present it. So I've been thinking about attractiveness factor, so it's kind of work in progress, but basically we have a set of amenity types found on map. So this is like a doctor, a hospital, a university, and so on. And then I have classes because I want to have something like 8 dimensions of attractiveness, or I could say I want 20, but I want to somehow integrate data. I'm saying if there is a high school and public and primary school, they are both educational institutions. So I want to integrate into one factor. Okay, so I'm somehow trying to do it. So then I'm saying that I have some classes, and I have also a range. So if it's a university, I would be saying that if it's close to the university, it's like 10 kilometers and it's still close to the university. But if it's kindergarten, it's maybe only 2 kilometers and it's close to the kindergarten. But if you have kindergarten 10 kilometers away, it's very far. So it depends on the type of the educational institution or the type of amenity. What does it mean close? If it's a grocery store, a close grocery store is like half kilometer. But if it's a big shopping mall, if you can, you know, drive in 5 minutes, you also say it's close. Okay. So, how do you choose this scale? I just made it. I just made it configurable. So this is a configuration file in the project. Okay, but I'm saying there exists a scale. I'm like kind of not, so for visualization, I will be showing you in a second, some scale has been used, but it's arbitrary, okay? Because I made decision making kind of common sense. So then I have the attractiveness measure, where basically this is the, so X is a node of a, X is a location on a graph, so X is a location in a graph. Now for it's a specific U is a location of a graph and X is a specific amenity, and each amenity has some type of power of influence. So P stands for power of influence. So I have some power of influence. I have some range of influence, and I have some distance. So I have power of influence, a range of influence, and distance. So basically this is a power of influence weighted by the range, and I'm aggregating it. Maybe I should be using geometric mean or something else, and I'm just adding it just for, you know, for the initial version of the project. But basically what this is saying, that I'm looking at a location, I'm looking to distances to all hospitals or through all shops and so on. And for each shop that is quite nearby, I'm scoring points, and I'm collecting, aggregating on the points. So this is just a very simple measure for that. Okay, so this is my attractiveness factor. Okay, and now some images. So if I have this attractiveness factor, so this is my map of Toronto. There will be other maps as well soon. Okay, okay. I will start with beautiful map I got from Anshul. Just very so Anshul has also processed this data, so maybe it's better to start with that. So here we have the entire Toronto metropolitan area. So there are 3 measures selected here: restaurants, parking, and transport. And of course, you can even see here the shapes of Toronto Transit connection here. So this is the availability of transport. So the area that are more dark, they are better for transportation. Here we have the area around, here we have the area, the colors are maybe not seen here very well. Here we have the area around Fields Institute, yeah. Yes, the projector is not representing the spot, but this is kind of multidimensional. So I was trying to make each dimension. So this is education. So there are, you know, in the center of Toronto, you have universities, and they make accessibility of education nice. Then this is entertainment in the Toronto area. This is healthcare. There's an amazing amount of pharmacies. So pharmacies make lots of healthcare points. So this is availability of healthcare. This is availability of leisure, parking, restaurants, shopping, and transportation. So actually I got a map of TTC automatically, kind of looking at the availability of transportation and making the visibility just by accident. If you know the shape of London TTC, this matches the shape. Okay, and then what I did, I tried to, then what we did, we tried to put those attractiveness measures on the graph, because underlying I have the graph representing the space of the city. Okay, and so far the only thing I could easily do is for each edge to put in the middle of the edge as a weight. So edge is like a piece of road between points A and B, to put as a weight of the edge, the attractiveness of that location, and then try to do graph clustering to see actually if have clusters of, say, living communities around some location. And I tried to do this. It's on road system. So now there will be only nodes, no edges, okay? Because edges is the road network. So you are seeing the edges like here on the map. Okay, so this is So these are Leiden communities generated on the central area of Toronto using this attractiveness of the public transportation. And if you look on the previous slide with the map of public transportation, this was I lost it. Where do I have it? This one, if you look at the middle of this map, like here, the middle part of this map. So remember the shape here. I'm not sure how it's well seen, but you can actually see that this clustering is corresponding to transportation lines. So it's getting somehow, so here is some line, and here are isolated vertices because they are very far already from public transport. You have to walk too far in the terms of my model. So I'm not plotting here isolated vertices because of the readability. It's only vertices, the underlying edges is the map. Okay, but then I got